Welcome in this video, and today I am going to discuss about the processor status and the flag registers of 8086 microprocessor. So you know the central processing unit in a microprocessor can make any kinds of decisions on the current state of the microprocessor and the flag register in the microprocessor, in the 8086 microprocessor, can be classified into status and status flags and control flags. So 8086 microprocessor, the locations of status flags are 0, 2, 4, 6 and 7 and 11, and the control flags which locations are 8, 9 and 10. You see in this figure. So in the status flag, if we talk about the status flag, then carry flag, parity flag, carry flag will be 1 if there is a carry out in the MSB on the like addition, or when you are taking borrow from the MSB on, in the case of subtraction. Parity flag will be 1 if your low byte, you see here, your low byte of a result has an even number of 1 bits. So the result, if it is 1 number, then it will PF will be 1. It is 0 if the low byte has odd parity, that means number of ones has odd parity. Okay, and so here you see the flag names and their bit positions and their symbols in 8086 microprocessor. So now I am going to discuss the 0 flag, like ZF equals to 1, auxiliary flag. So when the flag will actually contains 1 or 0. So ZF, like as for example, 0 flag will be 1 when your result will be 0. Sign flag will be 1 when the MSB result will be 1. Overflow will be overflow can occur in the signed and oversigned, signed and unsigned overflow. So now I want to see, we would like to see how the overflow actually occurs. So you know the numbers actually represented in a computer in a signed way, in a signed or unsigned way. So in the for 16-bit words, for 16-bit, that means one word, which is for unsigned numbers, is represented as minus 32,768 to 32,767, and 8-bit representations and 8-bit representation for signed number is minus 128 to 127. On the other hand, if you see the signed numbers, which is represented, because there is no negative number in here, so unsigned number will be represented for 16 bits is 0 to 65536, whereas 8-bit it will be represented as 0 to 255. So if you see this example sorry so there are, so when we perform an arithmetic operations like additions, so here you see there are 4 possible ways, there are 4 possible outcomes, like no overflow, or it can signed overflow or unsigned overflow, or both signed and unsigned overflow occur in your operation. So there are different kinds of scenarios which I will explain using example. Here you see an example where AX register contains FFH and BX also contains a value, and when we are adding this, those values, that means in these operations, you see the correct answer is 1000H 65536, which is already overflowed, like, because our range for signed overflow was 0 to 65535, but the number is now you see the 65536, so it is out of range. And AX will contain actually 000H because the carry out, that is actually the bit number is overflowed, so the result is 00, but it is not actually the correct answer, it's a wrong answer. And if you see the unsigned overflow occurred, so the stored value in correct as assigned number, you see here the FFH is actually a -1 if I represent it the unsigned way. So unsigned number FFH is a negative number, so it will be -1, and 001 it's a 1, so -1 1, when you are adding, then it will actually, the result will be actually 0. So signed overflow actually did not occur, but unsigned overflow occurred, you see, in this, for this particular situation. And if you see the another example where your AX and BX both contains 7FF hexadecimal number, so if I add them, and here you see the signed and unsigned decimal interpretation of 32767. So when I am adding these two numbers, sign number 65534, that means it's not outside of range, it's inside the range, so no signed overflow actually occur in these operations. But unsigned overflow, that means here actually I am giving them a two positive numbers, but when you see the output is actually the -2, which actually a sign change, that means the signed overflow actually has already occurred. You see, in these situations the scenario is different. Here no sign of unsigned overflow occurred, but the signed overflow actually occurred in here. So how your microprocessor actually indicates this overflow? So this is very simple and important. When your signed overflow occurred, then OF will be 1, and when your unsigned overflow occurred, then the CF will be 1. Okay, so now I'm going to see you, and this is the unsigned overflow and signed overflow representations, and there are some examples in here to understand the signed overflow. So I have already talked about these things, but you can still read those things to better understand. And here how the instructions actually affect our flags. So here actually some instructions you are saying move and exchange. We know these two different instructions. I have already talked about in chapter 4 to discuss both of them, but here you see here we are studying how actually what will the effect in 8086 flag register 8086 microprocessor. If it is move exchange, then none of the flags will actually affected, but when you are when your operation is add or subtraction, then all the flags will be affected. If it is increment or decrement operations, so all the flags will be affected except carry flag. And negative operation, actually all the flags will be affected also, and CF will be 1 unless result will be actually 0. So now I am taking you to an example. Here you see X and PX. There are two registers and which contains two values in here, the same value actually. So after adding these operations, the result will be like this. So here sign flag is 1. Why sign flag 1? Because the most significant bit in your result is 1. Here you see F, 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 E. So the F actually the first MSB bit is 1, right? So SF is equals to 1. That means because the MSB is 1, so SF is 1. Parity flag is 0. Why it's 0? Because you have 7 odd numbers. If it is even 6 numbers, even 1 bits of 6 numbers, then it will be PF is equal to 1. Okay, that means it's odd parity. It means PF equals to 0 means 0 means it's odd parity. ZF equals to 0. Why it's 0? Because your result is not 0. Okay, if your result is 0, then ZF will be 1. CF equals to 1 because carry out, yes, there is a carry out 1. So after adding these contents, so CF will be 1 and OF is 0. Why OF is 0? Overflow flag is 0 now. So here you see the sign of the stored bit, as that of the numbers being added. So here you see that your result when you are adding the numbers, the number bit was FFH means it's a negative number, FFF hexadecimal it's also a negative number, two negative numbers, and your sign is not changed. It's the sign, but that means the result of your sign is also a negative number, so no sign change, that means no overflow occurred in here. Now if I give you another example, like add ALBL, and AL and BL both contains 80H hexadecimal number, and here you see the SF equals to 0 because the MSB is 0. You see your MSB is 0, so no sign flag, actually SF will be 0. And if you see the PF equals to 1, parity flag 1, because all the bits in the results are 0, so even number of zeros in here, so it can be it will also means the even parity, and your PF will be 1. And then ZF equals to 1 because the result is 0. Yes, your result is 0. Now ZF is 1. You see, in the previous example it was ZF equals to 0, and CF equals to 1 because there is a carry out. So OF equals to, why OF is now 1? Because the numbers being added are both negative. You see 80H and 80H both are negative number, but your result is 0, 0. That means the sign change, right? So for that reason OF will be 1. When your sign is changing, then the overflow flag will be, of course, it will be 1. Now another example, subtraction ax bx, and here you see the ax contains 800 and bx contains 001 is. So 001 is actually a small number, compared to your 800 hexadecimal number. So here actually it's a 800 is a big number and it's a small number, so the result will not be negative, right? So here sign flag will not, of course it will be 0 because there no MSB is 0, because your no MSB is 1. So PF equals to 1 because I think you know, I don't discuss it again. ZF equals to 0, you understand very well now, and CF equals to 0. Carry flag is 0. Why? Because a smaller unsigned number is being subtracted from a larger one, so no carry will actually come. Now overflow flag is 1, you see. So here if you analyze it in a sign sense, so we are subtracting a positive number from a negative number, because your 7FFF, sorry, yes, because you are subtracting a positive number from a negative one, so which is like two negatives, that means it's 800 is a negative number, and minus 00 minus means it's also it already a negative number. So when you are adding two negative numbers but your result is positive, you see here 7FFH, the first bit is 0, MSB is 0, that means it's a positive number. So you are adding two negative numbers and it should also a negative number, but when you are after finishing your operation, then you see, oh, the result is not a negative number, it's a positive number, so sign changed. So if your sign has changed, then overflow flag register will be 1, okay. And then increment AL operation, and AL contains a value like FFH, so we know the increment operation. So after incremented here, so here you see also the flag register have changed, okay. You see the flag register SF, PF, ZF and CF all are changes actually. YF equals to 0 here, Y equals to 0 because the numbers of unlike sign are being added in here, okay. And if you see the next example, move x comma -5, which means actually you are moving something, so none of the flags will be affected in your move or exchange operations. If you see the another example, negate operation ax, negate means your sign will be changed. If you compute a positive number, so after negative operations, so it will be a negative number, or if it is a negative number, so negate operations it will be a positive number. So now we want to see an example here, 800H. When you are doing negate operations in here, your result is again 800H. It's a magic number. You see the result, the negative operations is also same, which is actually exactly same as your input. So the result actually is stored for AX for sign flags are SF equal to 1, PF 1, ZF 0. Carry flag will be 1 because negative number CF will always be 1. This is our actually condition, which I have already told in very beginning of this lecture. And OF equal to 1. Now OF equal to 1 because the result is 800H. And when a number is negated, we expect that the sign will be changed. But in this example, you see that sign is not changing. For that reason, your wave flag will be 1. If your sign changes, then wave will be 0 for these operations, for negate operations. So I think you guys understand the flag registers and flag registers. And when microprocessor doing something or executing the instruction, then it always checks the status flags and control flags in the microprocessor. Okay. So this is a debug program which you if you see the example, then it will help you to understand how the program actually what are the memory actually contains, and how the memory actually how the contents of the register value is changing. You can see it see in this example. So okay guys, this is all about today. So take care. Allah Hafiz.